Hello there. We have already looked at, over the last many lectures, looked at dynamics of single degree of freedom systems. Then we looked at dynamics of generalized single degree of freedom systems. And finally, we were looking at dynamics of multi degree of freedom systems. And now, I am going to come to the last part of my course, and that is going to be an introduction really. I would just call it introduction because this field is actually a very large field. So, we are going to be introduction to dynamics of continuous systems. See, up till now we have been looking at discrete systems, single degree of freedom, 1 degree of freedom, multi degree of freedom, n degree of freedom, okay, or generalized single degree of freedom was the closest that we came to looking at a distributed flexibility kind of a system. Okay. But of course, there also we said that look, we are going to assume that it is subjected to a particular kind of shape function. Now, this time we are going to start looking at actually, let us look at a situation, and that is a bar. A bar which I will first look at what are known as axial deformations. So, axial deformations are this motion. Okay. The reason why I am starting off with axial deformations is that it is actually a very simple problem to solve, and then we will see, we will look at flexural, because we have looked at flexure in generalized single degree of freedom problem. Right now, we will just look at axial. Okay. So, now the point here is that if I were to deal with this, see, so this one has, this is the thing, and I do not know, well, let us just define for axial, the axial rigidity is given in this form, and I have m bar x dx. Okay, these are kind of standard things. Okay, and the question then becomes that we do not want to give, we will talk about the boundary conditions later. These we will see that these are actually a class of boundary value problems. Okay. So, anyway, so this is the thing, and if I were to look at it from the perspective of a single degree of freedom, what would I say? I would say that look, this is my u, and I would say that look, u of x is given by some xi of x of u, and then write the entire equation in terms of xi x, and just it will become a generalized single degree of freedom. No, I shall not do that. I shall not do that. I will not make this assumption. I will say that look, u x of t, which is displacement at any point, let me start x from here, u x of t is unknown. Now, if u x of t becomes an unknown, you see what happens is, then you have a situation where what you are saying is that look, the displacement at every point is an unknown. Okay? So, if displacement at every point is an unknown, this becomes an infinite degree of freedom problem, and this is actually a continuous problem. Okay. So, let us look at this. So, I am looking at axial deformations. So, I have a situation in which I have this bar and it has E A x and m bar x, E A x as the axial rigidity and m bar x as its mass per unit length. Okay. So, if I take an infinitesimal length, okay, what do I have? I have axial force P, I have this is P plus del P by del x. Why? Because P is a function of time. So, obviously, this is function of x and time. So, it is del P upon del dx into dx. Okay. And this is an elemental dx. These are the forces, and on top of that, okay, you have inertia forces. These are what? Inertia forces. Okay. So, if I look at the equilibrium of this, what do I get? I get the following: P plus del P by x minus P minus f I x of t is equal to 0. This is what I get my function as. Okay. Now, let us look at what f I is going to be equal to. Now, what is del P upon del x equal to? Let us see what P, how can I put it in terms of u x of t. So, if you look at it, okay, by definition, you have del P by del x is equal to A into del sigma by del x, because it is supposed to be uniformly distributed. Okay. Now, del sigma is equal to A del epsilon by del x. Okay. Actually, actually no, because A can also be a function. So, actually these go inside this. So, it becomes actually del P upon del x is equal to del E A epsilon by x. Okay. Now, the trick is the following, and that is that, and what is f I? F I x t, if you look at it, is equal to m bar dx into u double dot, which is actually del squared u by del t squared. Okay. So, that is f I, and here this one cancels out, this one comes out this way. So, what you have is it becomes del p x. So, it becomes del of del x E A del u by del x, because epsilon is del u by del x. Okay. Then you have the f I okay, here. So, this becomes a what? What does it become? It becomes then your minus m bar del u by del x t squared. This is u into dx, by the way, okay, into dx equal to 0. The dx exists in both places, and dx cannot be a function. So, we can write this equation in the following format: m del squared u by del t squared minus del by del x of E A del u by del x equal to 0. So, this become the partial differential equation for axial vibrations. Now, let us try to see how do we solve this problem. Well, this problem has to be solved in using two things. One is we need boundary conditions, we need initial conditions. What are boundary conditions? We need to know u at 0 of t or u dot at 0 of t and u at L of t, that is the boundary, or u dot at L of t. So, these are the boundary conditions. And what are the initial conditions? The initial conditions are u at x equal to 0 and u dot at x equal to 0. These are the initial conditions, time t equal to 0, boundary conditions at x equal to 0 and x equal to L, okay, or any other point. Okay. So, let us take this particular thing. So, this becomes m bar del squared u by del t squared minus del by del x E a del u by del x equals 0. Okay. So, this becomes the vibration problem. Okay. So, now let us look at this particular thing and let us have a situation where let us put it in that I have this bar. This is a bar which is fixed at one end and free to go at the other end. So, what do I have? Then my boundary conditions are the following, and I am going to take x from here. So, my boundary conditions are the following: u at 0 t is equal to 0. And look, the over here the axial force is equal to 0. I mean, sorry, the strain is equal to 0 because there can be no strain at the free end. Okay. So, the other one is u dot L of t is equal to 0. Okay. So, this becomes the specific problem, and what you have is these are the boundary conditions. Forget about the initial conditions for now. Okay. We are not interested in the initial conditions, and what happens then is that you have this situation where let us see, and I am going to say that this is m bar constant, E a constant. So, it is a uniform beam with uniform mass distribution, and of course, E a is a constant because. So, then this equation becomes the following: m bar del u by del s squared minus E a del squared u by del x squared is equal to 0. Okay. So, now I have a situation that this becomes my problem to solve. So, this is for axial deformations. Okay. So, now how we solve these will come to later. Right now, I am just doing equations of motion. Okay. So, the boundary conditions, of course, and I forgot initial conditions. Initial conditions is u x 0 and u dot x equal to 0. And of course, what we can do is if we have any load on that, we can say that look, this is equal to some p x of t, some loading. Okay. That's neither here nor there. Okay. So, that becomes your axial motion kind of a system. Now, let us look at the case of flexure. I have looked at axial, now I will look at flexure. Okay. So, we will look at flexural deformation. And if I take any dx, what do I have? I have m plus del m by del x dx. Then I have v, then I have v plus del v by del x dx. Then I have load p bar x of t, and on top of that, since this is moving up in this direction, I also have f I. So, if I were to look at the two equations, what do I get? I get two equations, right? There is a force equation in this direction. So, if I look at the force equation, what I get is v plus del v by del x dx plus f I minus v minus p bar x t is equal to 0. That is this. And then if I take moments, what do I get? I get, suppose I take moments about this point. Okay. No, let us take moment about this point. Okay. So, what we get is m plus v dx, okay, minus m plus del m del x dx is equal to 0. So, these are the two equations that I get. Let us look at the bottom equation first. It is an easier equation to look at, and the easier what it says is, if you look at it, that the bottom equation, the second equation, says v is equal to dm by dx. Big deal. Static equation, right? Now, we also know that m is equal to E I into del squared u by del x squared. We know this. Okay. Now, the top equation gives us what? It gives us that del v by del x into dx plus f I. And what is f I equal to? F I is equal to m bar, okay, into del squared v by del t squared, because v is in this direction, u is axial deformation, this is lateral deformation. So, it is m into dx, okay, then minus p bar x of t dx, this is also p bar x, because that is the total load, is equal to 0. So, dx exists in all of them, and so I can eliminate that, and ultimately what I get is equal to m into del squared v by del t squared plus. Now, if you look at del v by del x, that means this is equal to del squared x of m. So, this becomes del squared x of E I del squared v by del x squared, right, equal to p bar x of t. This is the simple flexural deformations. Okay. Now, note something very interesting, and that I did not mention that, and that is that since you have in T squared a double differential, there has to be two initial conditions. Since you have a double differential in space x squared, you have to have two boundary conditions. Okay? That is de rigueur. Okay? So, here this particular problem, if I were to rewrite it, I will put it down properly, it becomes the following. It becomes m bar del squared v by del t squared plus del squared x e I del squared v by del x squared is equal to p bar x of t, initial conditions v x at 0 and v dot x at 0 have to be specified, and boundary conditions. Now, note that there is a fourth order. Fourth order means we need 4 boundary conditions to be able to solve it, and the 4 boundary conditions that you typically have are given in terms of v 0 t or v L of t, and the other boundary condition becomes v dot, which is the slope at 0 of t, or v dot L of t. You know, it's all, I mean, it could be any one of them, right? You have to have all told there are 4. So, it is this, then you have finally this is slope. So, it is del v by del x, del v by del x, and del squared v by del x squared at 0 of t, and del squared v by del x squared at L over t. Now, note that these are the 6. What are these corresponding to? These actually correspond to the moment boundary conditions. Okay? They are the moment boundary conditions, because similar to the one that you had over here, you had what boundary conditions did you have? The boundary condition was this. Why is this? Because this is actually, this is not strain, it is really the load, and there is no load here. So, the strain is equal to 0. Okay? So, similarly, this is really moment, because curvature is related to E I into moment. So, if moment is known, then you know moment, and out of these 6, any 4 will have to be known. For example, let me take a situation where what kind of boundary conditions do I get? Okay. If I have a boundary condition for this particular case, remember I showed you that if you have this, then boundary condition is given in this way. Suppose this was what would the boundary conditions in this particular case be? The boundary conditions would be u 0 of t equal to 0, u L of t is equal to 0. That is how the boundary condition would be. So, similarly, let us look at some typical kind of problems that we have, and we can actually look at the specific form of the boundary conditions. Okay, for example, let us take simply supported. What kind of boundary condition do I have in this particular case? And they take x from here. If I look at this, what I have is boundary condition here is that v of 0 t is equal to 0. I mean slope I have nothing to do about, but I know moment is equal to 0. So, del squared v by del x squared 0 of t is equal to 0. Here similarly, v of L t equal to 0, del squared v upon del x squared L t is equal to 0, because moment and deflection are 0 in this particular case. Suppose I have this. What do I get over here? Here, so these are the 4 boundary conditions for this. Here, what are the 4 boundary conditions? Let us see. V 0 t is equal to 0, del v by del x, no slope at 0 t equal to 0. Here, well, I know nothing about displacement, displacement can occur. I know nothing about slope, slope can occur, but there can be no shear. So, d cubed v by dx cubed at L upon t is equal to 0. Similarly, moment is equal to 0. So, d squared L upon t equal to 0. So, here you have kinematic boundary conditions, you have force boundary conditions. Here you have both kinematic boundary conditions, kinematic boundary condition and force boundary conditions at both ends. So, this in essence you always have to find out what your boundary conditions are in a particular case. Okay. So, you will always have to have, for example, let's say suppose you have something like this. You have this boundary condition. What would this boundary condition be? Well, here this over here will be the same as this. Okay? This one is exactly the same as this one. And what will be it here? Over here. So, at every place, at every point, you will always have 2 boundary conditions. Okay? So, here you have 2, and here what are the 2? Well, you can't say anything about shear, but you can definitely say the displacement. Okay. So, v at L of t is equal to 0, and what else? You know that the moment is 0. So, you know del squared v by del x squared at L equal to t is equal to 0. So, this is the way. Of course, these are known as what are known as homogeneous boundary conditions. We might have mixed boundary conditions too. I will talk about those later. But the point then becomes is that you have a situation where whether you have axial deformations or simple flexure, right now we are considering simple flexure, okay, you can always write down the equation for the axial deformation. It's given by m bar del squared u by del t squared minus del squared by del x squared Ea del by del x of Ea del u by del x equal to p bar x of t, where p bar is the axial loading. Okay, that's for axial vibrations. For the simple beam case, the equation turns out to be equal to m bar del squared u by del t squared plus del squared upon del x squared Ei del squared v by del x squared is equal to p bar x by t. And since you have every time you have a double differential in time, so you require 2 initial conditions. So, that is u at x equal to 0 and u dot at x equal to 0. Okay, these are the initial conditions, and typically we always start off with saying that, well, initial conditions are 0 at rest, so they are 0 at all times. Okay, so that's the initial conditions. For axial deformations, since you have del by del x Ea del u by del x, okay, you have double differential, so you require 2 boundary conditions. So, the 2 boundary conditions, if they are homogeneous boundary conditions, one will be at 0 t and one will be at L over t. You can always find out these Okay, so you'll always find out boundary conditions given the particular boundary that you have. And for flexure, since it's a fourth order equation, okay, you require 4 boundary conditions, and I've given you some typical boundary conditions, homogeneous boundary conditions that you are likely to have in this particular case. Okay. So now the question becomes, well, how do we include this was a simple case where there was no rotatory inertia, there was no shear deformation, anything. Okay. So in this particular case, how do we solve the problem? Okay. So in this particular case, well, let's look at it. I'll come back. This kind of a beam where you consider shear deformation and rotary inertia is known as the Timoshenko beam. Okay. So one, we have simple beam which we have looked at, where inertia is only linear and we neglect shear deformations. We are only considering flexural deformations. Okay. And then you have the Timoshenko beam, where I'll come to the Timoshenko beam a little bit later. Right now, let us not complicate the issue. Okay. So now let's look at, so these are the equations of motion. I have got a simple flexure and a simple axial. 1 bar boundary conditions, we know how to solve the problem. So now how do we do the dynamic analysis? Okay. Let's look back. For dynamic analysis, okay, before dynamic analysis, even for single degree of freedom, dynamic analysis dependent on the free vibration characteristics. Multi-degree of freedom, again we saw that the entire, if you use mode superposition, the entire solution process requires free vibration analysis. And here what we are going to do is we are going to look at free vibration analysis. So I've looked at equations of motion, simple beam. In both cases I've looked at a simple beam. I've looked at axial deformation and I've looked at flexural deformation. Okay. The Timoshenko beam, which is more complex, where you consider shear deformation, you can consider rotatory inertia. That's the most complex kind of beam solution that you can get. We'll look at that. We'll look at that later. Okay. So right now let us look at the kind of situation where we have free vibration. We look at free vibration. And to begin with, I'm going to start off with free vibration. In axial deformation. I'll start off with that. Okay. So let's see what the free vibration is. When you have free vibration, this is the equation that you have. And I am considering that EA is a constant. Okay. Let's look at this particular format. Okay. So now to solve this in a partial differential form, we have to make the assumption that u x of t is equal to some, let me call this xi x. Now this xi x is not known, xi x into y of t. So what I am assuming is that this, now note that this is completely different from what we had done in the generalized single degree of freedom. In the generalized single degree of freedom, we had started with the assumption that we knew this. Here, this is not known. All we are saying is that we start off with the saying that assume that the response is separable. Okay? Assume that the response is separable. If the response is separable, then what do I have? I have this kind of a situation. If I want to look at it, del u by del t squared becomes what? Xi x into because this is the only one, and del squared u by del x squared is xi double prime y x of t. So, if I were to put this equation into this, what do I get? I get the following. Let us put that down. Okay. So, I will put this in, I get m bar xi x y double dot of t minus E A and del squared x. So, this becomes xi x y of t is equal to 0. Now, let me put this through by divide throughout by xi x and y t, xi x y t. So, if I divide by xi x y t. If I divide that, what I get is the following: m bar y double dot upon y t minus E A xi I x upon xi x is equal to 0. This is what we get. Now, note something very interesting. This is only a function of t, this is only a function of x, and the only way that you can have a function of t minus a function of x equal to 0 is that if both of them were equal to a constant. So, in other words, if I were to put down m bar, this could only happen if you had this equal to E A xi I upon xi x is equal to some constant c. Okay. And for now, I will call that as minus c. I will explain why I am putting that as minus c. Okay. Some constant. Okay. If we put that, then you see this becomes equal to 0, and because this is a function of t, this is a function of x, there is no way that they could cancel out at all instants of x and t to be equal to 0. The only way is that they were a constant. And the reason why I put minus constant will become obvious now. Okay. What happens is you get this kind of a situation. You get the following. You get m bar y double dot, okay, plus c y bar is equal to 0, and the other equation becomes E A xi prime plus c into xi x equal to 0. Okay. So, now if you look at this, what does this give me? It says that look, omega squared is equal to c upon m. Okay. And I will say fundamentally I will call it another term b squared, okay, because this is again the same kind of a problem as this, excepting that it is a function of x. So, I will say that b squared, another term, is equal to c upon E A. Okay. So, then c is equal to m omega squared. Okay. So, if I put m omega squared here, what I get is b squared is equal to m omega squared upon E A. Okay. Sorry, m bar, of course, this is all m bar. Okay. So, this is what you get. Okay. So, if you get here, you get y of t to be a1 sin omega bar t plus a2 cosine omega bar t. Okay. And what A1 and A2 you get from the initial conditions, and you get xi x is equal to B1 sine Bx plus B2 cosine Bx. And for these you incorporate the initial conditions. Okay. So, so if you have a situation where you have, so now let us look at the particular problem that I was looking at. Okay. If you look at that particular problem, you get the following. You get a situation where the boundary conditions tell you that this is going to be, what are the boundary conditions? That u of 0 t is equal to 0, and the other one is that u dot L of t is equal to 0. So, now let us look at this. Okay. Now, t is not a function, so I can just say, I can separate it out and say, look, xi of 0 is equal to 0, and xi this is prime, not dot, xi prime at 0, this thing is equal to 0. So, from that I can find out my, this is B1 sine Bx plus B2 cosine Bx. Now, if xi is equal to 0, put xi equal to, this is xi equal to L equal to 0, xi prime. So, xi at x put equal to 0, this one turns out to be 0. So, B1 into 0 is 0, plus B2 into 1 is equal to 0. So, from that we found out that B2 is equal to 0. So, that means xi x is of the form B1 sine Bx. Now, we differentiate this. We differentiate this, and what do we get? We differentiate this, we get B1 into B cosine Bx is xi prime, and I am going to put so xi prime L is equal to B1b cosine B of L is equal to 0. Now, note that these are not 0. So, for this to be satisfied, you have to have a situation where the cosine BL is equal to 0. And when is cosine BL equal to 0? Cosine BL is equal to 0 when BL is equal to n pi over 2. That means B is equal to n pi upon 2L. Okay. Now, we have already done that B squared is equal to m bar. So, now let us plug that in, because we found out the value of E. Okay. So, let us kind of try to see what we get. We get, see, B squared, we know that B squared is equal to m bar omega squared upon EA, right. And if we look at it, this implies that omega squared is equal to B squared EA upon m. That means omega is equal to B square root of A by m. Okay. And B, I have seen, is equal to n pi by 2L. So, omega is equal to, so this is equal to, where am I? B squared. So, I will put this in. So, this will going to be equal to omega n is equal to n pi upon 2L into square root of EA upon m bar. Now, this EA is a unit, so I am going to put L inside. So, this becomes n pi by 2 into EA m bar L squared. So, omega 1 is equal to pi by 2 square root of E A m bar L squared. That is omega 1. Omega 2 is equal to 3 pi by 2. Sorry, this is 2n minus 1, huh? Because 2 becomes pi. Pi is not, so it's 2n pi. So this is 2n minus 1. Okay, so this is 3 pi E A squared m bar. And let us look at the interesting part, and that is okay. So what is xi x equal to? See, we are not interested in initial conditions, so we are not going to consider. So if you look at it, xi x becomes equal to b1 sin bx. So this one is nothing but sine 2n minus 1 pi over 2l x. So that one I can say is equal to sine 2 so psi n is equal to 2n pi over 2 x over l. Okay. So therefore, if I have omega 1 and that is equal to pi by 2 E A m squared, the corresponding mode shape, and note that this is mode shape xi 1 x. Okay. The corresponding mode shape is equal to sine pi by 2 x by L. Okay. So let's see how that looks. How does it look? Of course, note that I am going to draw u, which should be drawn in this direction. I am going to plot it. Okay. Sin pi by x at x equal to 0 is 0, and at x equal to L, it is sin pi by 2. So, it is 1. Okay. So, it is this is the displacement. So, it is in this direction. I am just plotting u. Okay. So, this is equal to 1. Okay. So, that in a sense is my mode shape. You see, I have got my frequencies and mode shapes. Okay. So, omega 2 is equal to 3 pi by 2 E A upon m bar L squared, and the corresponding mode shape is pi by 3. So, therefore, it is going to be in this. So, it is going to be this way 1. Okay, because 3 pi by 2 it's minus 1. Okay, so that's how I'm going to. The point is, note the initial mode is a simple mode. Okay, it's a simple mode, and the second mode has one node. Okay, if you plot this third one, 5 pi by 2 E A upon m bar L cubed, you will see that it will be 5 by pi. So, it will go here, and so it will be there are two nodes. This is a factor that you have to notice, that if you are looking at a particular situation, the first mode, no node. Node is where there are no displacements. Second mode, one node. Third mode, two nodes. Fourth mode, three nodes. This is how it goes. And this is the free vibration analysis. And we have got the mode shape. Only thing is that we have got the exact mode shape, because we have solved the partial differential equation in this particular case. Okay. So, now, this is for the actual vibration. Okay. Similarly, I will just write down the equation that I have, and that is going to be equal to, let us look at the simple flexural vibration. Simple flexural vibration is what? It is given in this format. It is given as m del u by del t squared del V plus EI del fourth by del x fourth is equal to 0. Now, let us take the situation where I have the following. I have again my Vx of t I take as xi x y of t. So, if I take it this as, then what do I get here? I get m bar del squared becomes just y of t. So, it becomes xi x y double dot of t plus E I, and here I have del fourth. So, I have the fourth x y t equals 0. Again, I am going to divide throughout by this thing, and so what I get is m y double dot upon y, okay, plus E I fourth upon xi x is equal to 0. So, what we get is the only way, again you see, the only way that a function which is only a function of t and a function of x can be is if they are. And so, if I write this in this fashion, minus E I xi fourth upon xi is equal to minus c. So, then what I get is I get the following equations. I get the equation to be m y double dot plus c y is equal to 0. Okay. That gives me the fact that y of t is of the form a c upon m. So, that is like omega squared, omega t plus a2 cosine omega t. These you can find out from initial conditions. The other one is a more interesting equation. It says E I fourth. Okay. So, that is actually d fourth by d x squared. So, that is the one. Okay. This minus this. So, this becomes minus c phi is equal to 0. Okay. And this one we are going to look at a little bit later. Okay. So, how to solve this one we will see. Okay. This becomes a much more interesting problem. Okay. We will see it next time. So, the point that I am trying to make is, today what we have done is we have looked at overall equation of motion, two equations, simple ones, axial deformation and simple flexure. Okay. Then what we have looked at is free vibration, and we have seen that for axial deformations you require 2 boundary conditions, and for flexural deformations you require 4 boundary conditions. Okay. And then when we solve the free vibration equation, the axial I showed you that you get lovely omega and the corresponding phi. Okay. And the first frequency has the mode shape has no nodes, etc., etc. And then we went through the process of the flexural deformation, and we saw that you get a very elegant formulation. We will solve this formulation in the next class. So, right now I am going to stop. Thank you very much. I will talk to you later. Thank you. Bye.